Suppose you have a 0.75 kilogram object on a horizontal surface connected to a spring that has a force constant of 150 newtons per meter. There is simple friction between the object and surface with a static coefficient of friction of 0.1. Letter A, how far can the spring be stretched without moving the mass? All right, so for letter A, we have to take a look at these two pictures. The first picture details the spring before it is stretched. All right, so here's some fixed, well, it's a movable object, but the spring here is going to be fixed to that black movable object. It's connected to a block. The block has the mass of 0.75, the force constant of the spring is 150, and the coefficient of static friction between the block and the horizontal surface is going to be 0.1. Now, what's going to happen is they want to know how far can we stretch this spring before the block moves. So we know that it'll be able to stretch a little bit. Why? Well, because there's some friction here, right, that will be opposing then the force pointing to the left. So I wrote it out now in the second case. As you can see, the spring has been extended, okay? And I just now wrote in what the change in now displacement is for the spring, right? The spring was stretched by X amount. Okay? And what they're saying is they want us to calculate this X. How far can it be stretched? All right? Before the block begins to move. So this is a basic force problem. So what we have to do in the second case here is detail all the forces that are acting on this particular block right here. So I'm going to draw a free body diagram. All right? The easiest thing to note is the force of gravity, right? I mean, gravity's pulling it down. So we know that the weight, I'll actually just write F sub g for force of gravity. Now, the force of gravity will be opposed by what? Well, since it's resting on a horizontal surface here, it's opposed by the normal force, right? So that's going to be pointing up. Okay, good. Normal force, Fn. Now, what is the applied force in the problem? In other words, here, what is the force that the spring is applying to the block? In what direction, I should say? What direction is this force being applied to the block? Well, it's being applied, if you think about this, right, the spring is going to be pulling on the block to the left, right? Since it's stretched, the spring's going to want to recoil and pull back to the left. So therefore, I know that we'll say the force that the spring is exerting is going to be pointing to the left. Now, that leaves only one other force that's in the problem that I didn't detail yet, right? It's the frictional force. Why is there friction? Well, because they told us, right? Otherwise, we may have assumed that it's frictionless, but they told us that there's friction. So where is the friction pointing? This is the key. The friction is pointing to the right. Why is it pointing to the right? Well, it's going to oppose. Remember, friction always opposes motion. So the natural motion of this block, when it is stretched, is going to be to the left, right? If it were frictionless, wouldn't it begin to move to the left as soon as you started pulling the black part to the left? And therefore, friction opposes that. So you know the force of friction has to be pointing to the right. Okay? So force of friction. Now, we have a full free body diagram here. Okay? What I now need to do is I now need to realize that if I want to find out how far the spring is stretched, I basically am talking about the pure X axis here, right? I mean, I might have to do some Y substitutions in there as well, but I'm really talking about the pure X. So basically, I can now state that the sum of the forces in the X direction should equal 0. Why? Well, first of all, the sum of the force in the X direction always equals mass times acceleration. Okay? However, is the block going to move? No. So what does that mean the acceleration is? 0. So that's why now I can state this, that the sum of the forces in the X direction is equal to 0. Now I ask myself, according to my diagram, what are the forces in the X direction? Well, I got this force of friction pointing to the right, so that's positive. I got this then force of the spring pointing to the left, and therefore that's negative, so I'm going to plug it in just like so. And now what I realize is I can equate these two together, right? I can basically say, and this is what we should expect, that the force of friction should be equal to the force that the spring is exerting on the object. All right, now this is the important insight. From here now, we can begin to expand on these forces, right? You might get to this point and say, well, this is great. Now where do I go? Well, we have to expand on these now variables. So the force of friction, you have to memorize this from way back when, right? The force of friction is equal to the normal force, I'll say. Actually, I'll do coefficient of friction. Now, in this case, it's static friction since it's not moving. multiplied then by the normal force. All right, so that's the formula. So now what I'm going to do is expand on that force of friction. So now I can write the force of friction is basically going to be the coefficient of static friction multiplied by that normal force. And that will equal now the force that the spring is exerting. Well, we have a nice little formula for that up here, Hooke's law. Right, it says that the force of the spring is equal to negative kx. So what I'm going to now do is plug in negative kx in for the force of the spring. And let's now see, do we know the coefficient of static friction? Sure, they gave it to us. It was 0.1. Do we know the spring constant? Sure, they gave it to us. It was 150. Do we know x? Well, we don't, so we have to calculate that. That's what it's asking. So we better know the normal force. Do we know it? Well, not exactly at the moment. But now what do we know about the normal force? Well, now I'm looking at my diagram, and that's in the y direction. So now I'm going to create this little thing, right? The sum of the forces in the y direction is equal to ma. Well, is the object moving in the y direction? No. So guess what the acceleration is? 0. Right? So the sum of the forces in the y direction will then be equal to 0. What are the forces in the y direction? Normal force, force of gravity. Up is positive, so the normal force is positive, minus then the force of gravity, that's negative. And look, lo and behold, we realize that the normal force is equal to the force of gravity. So guess what I can do now? I can take the force of gravity and plug it in for the normal force. All right, so that becomes now the coefficient of static friction multiplied by the force of gravity is equal to then negative kx. And then expanding on the force of gravity. What is the force of gravity? That's just the weight of the object, right? So the coefficient of static friction multiplied by the mass of the block times gravity, that will equal negative kx. And lo and behold, now I know everything. I know the coefficient of static friction. I know the mass of the block. Gravity is obvious. K, they told me. So now solve this thing for x, and we realize we're going to have a formula that works out to be negative coefficient of static friction multiplied by the mass of the block multiplied by gravity. And this is all divided now by, this will be all divided by the K, right? The force constant. Plug it all in. So negative 0.1 times then the mass of the block, which was 0.75, times then gravity of 9.8, all divided by now K. And K was, they told us 150, right? So now what we'll do is maybe I'll move this up just a tad. All right. Move it up just a little bit there. And now what I'm going to try to do is just plug in the value for x down here. So let's see. It's going to be negative 0.1 times 0.75 times 9.8, all divided by 150. And we get a value here of about x is going to be 0.0049, and it's negative. Now, according to my picture, that should make sense, right? The block, the spring has moved. It has displaced to the left. If I consider this my initial and then this my final, it has been displaced to the left. So the negative sign makes sense according to my picture. You could have drawn the opposite picture where everything is basically just the mirror image or the enantiomer if you've taken organic chemistry. So basically now your answer would have been then a positive answer. So then we're saying, well, what's right? Well, both are right. It depends on the picture. So what you can state is you can just give the positive answer if you so like. It doesn't matter. All right. According to the picture, my picture should be negative. If you want to just give the absolute value, that's fine. How far can it be stretched? It can be stretched by the positive value, right? Of 0.0049, and that's in terms of meters. You can convert that into millimeters if you need. All right. So that takes care of now letter A. Okay. Now let's see if we can start doing letter B. Let's move this maybe over just a tad. I'll try to put this all on one space. Just give me 1 second, guys. How you all doing today? Hopefully you all having a good day. Always a great day when we're doing physics, right? All right. So, letter B. If the object is set into oscillation with an amplitude twice the distance found in part A, the kinetic coefficient of friction and the kinetic coefficient of friction is 0.085. What total distance does it travel before stopping? Assume it starts at the maximum amplitude. There could be a few ways you can go about this. I'm going to do it the kinematic way. So what they tell me is that now this thing, so if this was, look at my picture, if this was the x value, what we're now going to do is stretch this thing twice that amount. All right. And they said to assume that that would be the amplitude, basically. Right. So what that means is as soon as they told me amplitude, I start thinking about the formula over here where it tells me then the maximum velocity is basically equal to radical force constant divided by the mass multiplied then by the amplitude. So what I realize is I can find Vmax. So why don't we just do that quickly? So the maximum velocity here will be equal to the square root of 150 all over 0.75 times in the amplitude, which was twice the displacement down there. So it's going to be 0.00. Oops. Let me just move this over a little bit. 0.0098. Okay. And now simply just calculate Vmax. So square root 150 over 0.75. Oh, wait, hold on. Square root of 150 over 0.75. Multiply that now by 0.0098. And we get a maximum velocity here of about 0.139 or so. 139 meters per second. Okay? Now, so that means that basically, after this thing is stretched over here and it's released, right, the block is then going to, I mean, it depends on what we consider to be stationary in this problem. We have to make some assumption there, okay? But we will assume that, yeah, actually it's interesting. Yeah, it might actually depend if you know, it might depend on what's the friction here. It's a rod. It didn't even tell me much about it, right? So part of the assumption here is that once this thing is stretched to the left, pretend it's just going to be totally fixed in position. Okay? If it's totally fixed in position, then what that will now mean is that the block will begin to move to the left. And what's the maximum velocity? Well, the maximum velocity is going to be 0.139 meters per second. And where is that experienced, do you think? Do you think that's experienced right at the start as soon as we release the block or something like that? Or do you think it's at the end? It's a good question, right? Well, it's actually not going to be at the start nor at the end, okay? However, it's actually going to be kind of in the middle, right? You know that as soon as this thing is released, it's going to speed up, right? And then it's going to reach a point and it's going to start to slow down. Now, the interesting thing about this is that we can assume, though, that if I'm calculating the maximum velocity, right, that we can basically now use this maximum velocity to help then us calculate the distance, okay? So watch. So what I can now do is basically, I know the maximum velocity, so I know this is essentially, I can call this the initial velocity. All right, is it the exact initial velocity? Well, not exactly, but I'm going to make an assumption here, and you'll see how it's going to work out. So we'll just call this the initial velocity. Well, what's going to be the final velocity, do you think? Eventually. Well, it told us how long does it travel before it stops. So we know the final velocity is going to be, I'll start writing it up here. We know the final velocity here is going to be 0. Right, the initial velocity we assumed is going to be 0.139. And then what we have left, if we want to find x, I'm like, well, wait a minute, what do I need to know? Well, I know if it's starting, you know, at some velocity and then it's going to end with some velocity, I know that there's going to be some acceleration in the problem, okay? Now, depending upon how you frame this, you just have to be careful with your values. But, you know, technically, if given my assumptions, the velocity would be to the left, and therefore this would be 0. Excuse me, this would be negative. But then the acceleration would actually be a positive value. All right. I know you're saying, well, wait a minute, it's decelerating. How's it positive? It's positive because the acceleration would be pointing to the right. All right. It's slowing it down. If it's moving to the left and it's slowing down, there has to be an opposing force pointing to the right. Does that kind of make sense? So how can we kind of understand that? Well, I can create another free body diagram, right? That details the block. So there's 3 forces now acting on the block. In this case, it's the weight of the block. It's going to be the normal force, and then the frictional force. Where's friction pointing? If the block, like I said, begins to move to the left, where's friction? It's to the right. Right? It opposes the motion. So notice here that there's going to be, and there is no force then on the left. We're going to assume that the spring, all that energy pent up in the spring is now translated into kinetic energy, basically. So now what I realize is I can solve this now and find the net acceleration. Now the net acceleration, if there's a vector pointing to the right, there's going to be a net acceleration pointing to the right. Okay? Now I know when I show the second way to calculate this, you're going to say, well, why the heck did you do it this way? And I'm not really sure. The other way would have been a lot easier, but hopefully you're still bearing with me. So we know that the sum of the forces in the x direction here will equal ma, and there will be some acceleration, so I cannot cancel that. So what's the force in the x? Well, it's only the frictional force, so I'm going to plug that in, frictional force, and it's positive, so I just leave it alone. And what's the frictional force? Well, I can break that down. Remember, it's the coefficient now of kinetic friction multiplied by the normal force. That's equal to ma. What is the normal force? Well, it's exactly opposed to the weight, and we talked about that already, so I'm just going to do the substitution times the mass of the block, right, or times the mass, then multiplied by gravity, and that's equal to the mass of the block, again, multiplied by acceleration. Notice what we can do here. Bada bing, bada boom, see you later, mass. And now what we have is we have a formula, and let me just move this up ever so slightly. We have now a formula that relates the coefficient of kinetic friction times gravity, and that's now equal to the, acceleration. So here now, we know what the acceleration is. So we actually will have a value for this. Why don't we just calculate it just to get out of the way? So this is going to be 0.085 times then gravity of 9.8, and that's equal to A. So why don't we plug it into the calculator? So 0.085 times 9.8, that's about 0.833, right? So this is 0.833 meters per second squared. Now this is positive again, okay? So when I plug it now in for my A over here, I'm going to write it as positive. 0.833 meters per second squared. Now, going back to kinematics, you got these variables. How do you solve for x? Right? We're going to use this formula. We're going to use the formula that Vf squared is equal to Vi squared plus 2ax. Okay? Way back when, right? Whew, way back when. So the final velocity is 0. The initial velocity will be negative. What do we have? Negative 0.139. The value here will then be, and that's going to be squared, okay? This will be then plus then 2a times x, right, times our x value. And now when we do the math here, right, we're going to bring the other term on over, square it, so we're going to get, 0.139, and that's going to be squared. So what do we have? We have a value now of 0.0193, I'm going cross-eyed at this point in the problem, is equal to then 2 times that acceleration, which we found was 0.833, times x. Right, so what's x? So simply just divide out now the 2 times that value. So take that, divide it now by, parenthesis, 2 times 0.833. And actually what I should do here, let me use the exact, what was the velocity? Hold on one second. I'm going to use the exact velocity. So so when I calculate it, just keep in mind I'm using the exact velocity when I'm squaring everything. So let me square that and then divide it now by 2 times 0.833. So we get a value here of about 0.0115. You thought I just left, right? 115. I just was double checking the calculation. Sorry. So there we go. All right. So this is now the x. Okay. So that's in terms of meters. Okay. That is in terms of meters. So that's the displacement. Or excuse me. Yeah, that is the displacement that the block will travel. Now, let me do this to you now. Let me erase some of the work on up at the top, and how else could I have thought about this? Well, I could have done this from an energy perspective, okay? It would have been a little easier, less work, but you would see that it's the same answer. So what I realize is that, again, when I calculate, a couple of ways I could do this. I can realize a couple of relationships that when this thing is fully stretched, all the energy in the problem is going to be potential energy that's inherent in the spring, okay? So the total amount of energy in the problem is going to be spring potential energy at the initial point, right? And all that energy that's initial has to equal then the final amount of energy. Well, the only problem is that the final amount of energy in the system is going to be absolutely zero, okay? Why is that the case? Well, because it stopped, so it's not moving, and it didn't change its vertical displacement, so there's no change in gravitational potential. So then the question is, well, where the heck did the energy go, right? Well, the energy went to friction. So basically what I can say is that all of this potential energy would have been converted into work energy done by friction. Or stating this another way, that the work energy of friction will suck all of the potential energy of the spring out of the system. Okay? So now what I have is I have a nice little relationship here where I can start expanding on this, right? So potential energy of the spring is 1/2 k times x squared equals now the work due to friction. Now you have to remember work is equal to the force of friction, right? Or just simply work is force times displacement, okay? And since I'm talking about friction here, the work due to friction is going to be the force of friction multiplied by the distance over which that force is exerted. So basically the question here is I got to find x. This x represents the distance that the object's going to travel. So I realize that I can reorganize this to kx squared all over force of friction. And that's going to equal x. Okay? Now expanding on this a little bit, I'm going to just write an equivalence over here that kx squared, remember x represents the amount of stretch in the spring. You got to remember that this is the displacement of this, so that's where it's going to get a little confusing. You might say, well, wait a minute, this x and this x, shouldn't they cancel? Well, not exactly, because this x represents, we're talking about potential in the spring. This is the stretched length, okay, of the spring, and this is the actual displacement. I'll put a little d here that it actually traveled, okay? So instead of maybe writing x sub d, let me just write d, all right? That should hopefully make it a little clearer. So that's d. All right, this is the stretch on the spring. So now I can simply write that the force constant multiplied by the displacement of the spring squared divided by the force of friction. What's the force of friction? Well, we can input now the coefficient of kinetic friction multiplied then by the normal force, right? But we know the normal force is equal to the mass times gravity. So I'm just going to substitute that in, mg. And now here we have our relationship, okay? Let's plug everything in now. And I'm going to do this whole thing on the right-hand side. All right, there's a little more space. So let's plug it in. So the distance here would have been equal to, oh, by the way, don't forget the 2 like I did. I just realized, right? Where did the half go? The half didn't go anywhere. Just seeing if you're paying attention. The half is still there. You can write a 1 over 2. So basically this whole denominator will be multiplied by 2, okay? Didn't go anywhere, just, you know, getting lost in my own problem here. So K is 150 times, I feel like I feel like I'm in Inception or something like that. I don't know. In a problem within a problem within a problem within a problem, and I can't escape. So this is 150 times the displacement of that spring. Now they said it was doubled, right? So this is the 0.0098, and that's squared. All then divided by now 2 multiplied by the coefficient of kinetic friction, so which was 0.085, times then the mass, which was 0.75. Let me put this in parentheses, and then that's times gravity of 9.8. And now simply throw it on into the calculator, and let's see what we get. Please work out to be the same, please, please, please. Divided by now 2 times 0.085 times 0.75 times 9.8. And would you look at that? So 0.0115 meters. All right. As you can see, they're both equivalent. So interestingly enough, this thing somehow is exactly identical to what I did over here. Right? So if I did all the substitutions, you probably would see it, but why don't you challenge yourself a little bit? Try to just do this whole part by doing just substitutions and seeing if you arrive at something like that. You should, right? And if you're even thinking about, no, there's no way. Well, look, there's a 2 in here, isn't there? Right? There's a 2. And where's the 2 found in this? Oh, here's the 2, right? So we have, you know, they're going to be equivalent. So try to figure it out. See how they are. All right? Again, thanks guys for tuning in. I know it's a long problem, but I think, you know, I want to show you more than one way to look at it. And, you know, hopefully that should help kind of bring the concepts, so to speak, together. There's multiple ways to solve a problem. The more tools you have to solve a problem, the better you'll be, the better problem solver you'll be. So, enough of the philosophy. Thank you guys. Again, please remember to help us out. If this problem helped you at all, please help us. All right? Subscribe, tell your friends, hit the like button. We can't thank you enough for doing that. Take care.